The fourth example has the same trigonometric functions, but the axis involved is y instead of x as previously solved. Welcome to Integral Calculus. The problem requires the area bounded by the first curves of the functions y as equal to cosine of x and another y as equal to sine of 2x, and the line x is equal to 0. The premise gives the functions of the curves y is equal to cosine of x and y as sine of 2x, and also the vertical line at x equal to 0. The rectangular plane used for this case has the y scaled with whole numbers and the x-axis are scaled in radians. Just like the others, the initial step is to sketch the curves to have an idea of the functions or where the differential element will end later on. And sinusoidal waves can be traced in two ways. One is through tabular substitution, when we look for the value of y assuming some values of x. Starting with y as cosine of x, we let x equal to 0, and y becomes cosine of 0, which is 1. When x is pi over 4, y's cosine of pi over 4, which is root of 2 over 2, or 0.707. At x of pi over 2, y's cosine of pi over 2, which is 0. Then, when we move to x as 3/4 of pi, y becomes 3/4 of pi, making negative root of 2 over 2, or negative 0.707. Then, with x as pi, y turns out as cosine of pi, which is negative 1. Trace the points to have the curve of y as cosine of x. Next is the second function, y as sine of 2x. When x is 0, y is sine of twice of 0, which is also 0. When x is 1/4 of pi, y turns out as sine of twice of pi over 4, which is 1. Then moving to x as half of pi, y is then twice of pi over 2, or that is 0. When x is 3/4 of pi, y is taken as sine of twice of 3/4 of pi, which is negative 1. Then, if x is pi, y becomes sine of 2 pi, which is 0 again. Trace the points to have the curve for y as sine of 2x. From the problem, what we are looking for is the area bounded by the first humps of these two sinusoidal waves and the y-axis, which shows two areas. The other method of sketching the curves is through analyzing the period from the equation itself based on the standard form y is equal to a times sine of the quantity b times x minus h plus k. I will reiterate once more that a in the formula gives the amplitude, or the height of the wave. H is the horizontal distance of the curve from the origin, and k is the vertical distance. The period is taken from 2 pi over b, where b is the coefficient of x. So from the first function, y as cosine of x, cosine has a coefficient of 1, which means the amplitude we are solving is 1, and the coefficient of x is 1, so the period is solved as 2 pi over 1, which gives 2 pi just the same. 2 pi is the wavelength of the function, which starts at 1 and has an amplitude of 1, so the curve can be traced as shown. The second function of y as sine of 2x has a coefficient of sine as 1, so the amplitude is also 1, and the coefficient of x is 2, so the period is computed as 2 pi over 2, or that is pi. So the wavelength of the second function is shorter as one full wave can be drawn in only pi distance. The areas bounded by curves and the y-axis are then identified. Step 2 is to identify if we are to use horizontal or vertical strip, where we are guided by the idea that the strip should touch both curves. Let's try horizontal strips first. The strips touch only one curve on the first area. Then there are chances that the strips on the second area touch the same curve. We then check the possibility of using vertical strips. Well, it shows that the vertical elements touch both curves on both areas, so we go for vertical differential elements. Step 3 is to identify the limits. Although we have an idea that we are to use x as 0 and x as pi over 2, there is an intersection which separates area 1 from 2. That is a limit we need to locate from the axis. We find the intersection by equating the functions y as y, or cosine of x as sine of 2x. The double angle of the second term can be transformed using double angle identities, making the equation cosine of x is equal to 2 sine of x cosine of x. The first method to simplify the equation is to divide everything by cosine of x, resulting to 2 sine of x as equal to 1. Sine x is then 1/2, where x is arcsine of 1/2, giving x as a sixth of pi. The other method to simplify the equation is to transpose cosine x to the other end and have 2 sine x cosine x minus cosine x as 0. Extract cosine of x and get cosine of x times 2 sine x minus 1 as equal to 0. Now equate cosine x to 0, where x is then solved as arc cosine of 0, which is half of pi. That is the intersection of the right. The other intersection is taken when 2 sine of x minus 1 is equated to 0. 1 moves to the other side and everything is divided by 2. So x is then arcsine of 1/2, which gives pi over 6. Proceed to the next step of generating the formulas using differential strips with their differential area of multiplying the length with the width. For the vertical strips, we have the area as y times dx, where y is computed as y upper minus y lower from the coordinate plane. The total area is then area 1 plus area 2, where the formula for area 1 is taken as the integral of the upper y, which touches cosine x, and lower y, which touches sine of 2x, multiplied by the width, which is dx. The limits are from 0 to pi over 6. The second area has its formula derived as sine of 2x minus cosine of x for its y upper minus y lower, then multiply dx. The limits for the second area is from pi over 6 to half of pi. The last step is to finally integrate the formulas to have the areas. Start with the first area with cosine of x minus sine of 2x times dx from 0 to pi over 6. Separate the integrals on each term, making area 1 as the integral of cosine x dx minus sine of 2x dx, where both have the limits from 0 to pi over 6. Analyze each term from here and get u as x on the first term. Its derivative is dx. Let u be 2x for the second term, where its du is 2 dx. So we adjust the integral by multiplying 2 to the second term's dx and balance it with 1/2 before the integrand. Now, The integral is ready for processing, which gives a1 as sine of x plus half of cosine of 2x from the limits of 0 to pi over 6. Now plug the limits and have the sine of pi over 6 minus sine of 0 plus half of the quantity cosine of twice of pi over 6 minus cosine of twice of 0. Cosine of 0 is 1. Cosine of pi over 3 is 1/2. Sine of 0 is 0, and sine of pi over 6 is 1/2. This can be simplified as 1/2 plus half of negative 1/2, or that is 1/4. The other function is next to be integrated, where the limits are from half of pi to pi over 6. Separate the integrals according to the terms, and get sine of 2x dx minus cosine of x dx from pi over 2 to pi over 6. Then analyze each term. The first has u of 2x, and its derivative is 2 dx. The second integral has u of x, and its du is dx. The first term needs a little adjusting. To have a derivative of 2 dx, we multiply 2 with dx and balance it out by placing 1/2 before the integrand. Integrate the equation to have a2 as negative half of cosine of 2x from 1/2 pi to 1/6 of pi minus sine of x with the same limits. Plug these limits and have negative half of cosine of twice of pi over 2 minus cosine of twice of pi over 6, then subtract sine of pi over 2 minus sine of pi over 6. Cosine of pi is negative 1. Cosine of pi over 3 is 1/2. Sine of pi over 2 is 1, and sine of pi over 6 is 1/2. Everything can be simplified as negative half of negative 1 minus 1/2 minus 1 minus 1/2. So a2 is 1/4. Now, the total area is just a1 plus a2, which is 1/4 plus 1/4, and that is 1/2 square unit.